I am Jawed Ahmad, Department of Mathematics, Jamshedpur Women's College, Jamshedpur. This is video 3. We have already presented two videos, and in this video we shall discuss or try to understand the concept of lower bound and greatest lower bound, that is infimum, with the help of different examples. Now we come to the definition. The set S is said to be bounded below if there exists a real number small m such that every member of S is greater than or equal to m. That is, x is greater than or equal to m for all x belongs to S. The number m is called lower bound of S. If no such number m exists, the set is said to be unbounded below or not bounded below. It can be easily seen that a set bounded below has infinite number of lower bounds. That is, a set bounded below constitutes an infinite set whose members are lower bounds of the set, and its greatest member is called greatest lower bound or infimum of the set. Like the supremum of a set, greatest lower bound or infimum of a set may or may not exist, and it may or may not belong to the set S. The infimum or greatest lower bound, that is GLB, M of a set S, has the following two properties. Number one, M is the lower bound of S, that is, M is less than or equal to x for all x belongs to S. Number two, no member greater than M can be a lower bound of S, that is, for a positive number epsilon, however small, there exists a number y belongs to S such that y is less than m plus epsilon. Now let us consider the following examples to understand the concept of lower bounds together with the least upper bound and greatest lower bound, and we shall see that there are some sets which has both GLB and LUB, and both are the members of this set, and we shall see there are some sets which are bounded below but not bounded above, etc. Let A1 be a set containing 4 elements, that is 1, 2, 3, 4. We see that 1 is less than equal to x, x is less than equal to 4 for all x belongs to A1. That is, all the elements are either less than or equal to 4 or greater than or equal to 1. This implies that least upper bound is the 4, which is the member of A1, and greatest lower bound is 1, which is also the member of A1. And this presents an example of that set which is bounded and whose both LUB and GLB are its member. We conclude that every finite set is bounded. Number 2, let n be the set of natural numbers. As you know, it contains positive integers like 1, 2, 3, 4 and so on. Here we see that there exists no natural number m such that x is less than equal to m for all x belongs to n. This implies that n is not bounded above, but x is less than or equal to 1 is true for all x belongs to n. This implies that GLB is equal to 1 belongs to n. Number 3, let us consider another example. A2 is equal to the set of all x such that 2 is less than x is less than 7. Clearly, least upper bound of this set is 7, which is not the member of A2, and greatest lower bound is 2, which is also not the member of this set. This example of the set presents that this is the set having both LUB and GLB, and they are not the members of this set. Let us take another example. Let I be the set of integers. Then there exist no integers capital M and M such that m is less than equal to x, x is less than equal to m, holds for all x belongs to I. As we know that in the set of integers there is no greatest member and there is no smallest member of this set. This shows that the set of integer is neither bounded below nor bounded above. That is, the set I of integers is unbounded. By similar arguments, it can be proved that the sets Q of rational numbers and the R of real numbers are unbounded. Now let us consider the following example. Each of the following intervals is bounded. You should know that interval is an infinite set. Interval always denotes an infinite set, whether it is open or closed or semi-open or semi-closed, etc. Let us take an example, open interval 2, 7, which denotes a set of all x such that 2 is less than x is less than 7, and this is an infinite set whose LUB is 7 and GLB is 2. Generalizing this case, you can say that the open interval whose end points are A and B is bounded, whose GLB is A and LUB is B. Similarly, the semi-closed open or the interval which is closed at 2 and open as 10 is bounded, whose GLB is 2, which is the member of the set, and its LUB is 10, which is not the member of the set. Like, this is a semi-open or closed interval, open at -5, closed at 12, is bounded, whose GLB is -5, not the member of the set, and LUB is 12, it is the member of the set. And generalizing this, you can say that closed interval whose endpoints are A and B is bounded, whose left point is the GLB and right end is the LUB. Both are the members of this closed interval. But the intervals A infinity minus infinity B both are bounded below and bounded above respectively, but both are unbounded because for a set to be bounded, it is necessary that set should be bounded below and bounded above both. Let us consider another illustrations to understand the concept of infimum and supremum clearly. Let A3 be a set of all 1 by n such that n belongs to the set of natural number, that is a set containing 1, half, 1 by 3 and so on. Here each member of the set is less than or equal to 1, which is true for all x belongs to A3. The set A3 is bounded above as 1 is an upper bound of A3. Also, any number less than 1 is not an upper bound of A3. Therefore, supremum of the set, that is A3, is 1, and which is the member of A3. Further, each member of the set A3 is positive, that is x is greater than 0, holds for all x belongs to A3. This implies that 0 is the lower bound of the set A3 and no other positive number is a lower bound of A3. Therefore, greatest lower bound of A3, that is infimum of the set A3, is 0, which does not belong to A3. Now we shall discuss the remaining topics of the real analysis in the next video, that is in video 4. And in this situation, stay at home and stay safe. Thank you.